Hi everyone, thanks for joining us. So we'll just started. So to mention, my name's John Walker, and I'm the head of architecture at ServiceHQ. And today I'm joined with Ed Sheet from Seldon.io, and he's going to take us through some of the details on dealing with machine learning at scale. So when you start deploying more than one model, and you've got hundreds or maybe thousands of models to deal with in production, how you can go about reducing the complexity of having to deal with that. And what I'll do just now is I'll make Ed the presenter.
Great, thanks. So I need to start sharing again, or can you see my screen?
Yeah, so I'm just going
to... Okay, there we go.
Should be able to share
that. Perfect. You just confirm that's all good for you, John?
Yep, that's good.
All right, great. I will we'll take it away then. So yeah, thanks for the intro, John. As we said, we're going to talk through some of the issues that arise, like when you're starting to do machine learning in production, what it looks like to scale deployments and handle those, and maybe some of the tips and tricks that we can learn from DevOps already and apply those for machine learning. The way I'm going to do this is I'm going to sort of tell a little bit of a story about like my own experience of going from a kind of like very much like a DevOps and my cloud architect role with an interest in machine learning to now working at an MLOps company full time, and what I've learned along the way. So we'll start with a little bit about me. I know these slides are boring, everyone does them, right? So that's me. I love pizza, and I play this weird sport called lacrosse, which goes down well with the North American fans because it's a North American sport. But I think within the UK, not many people have heard of it. So yeah, I play a lot of that. I love eating pizza. Try to make my own as well, not very successfully. I've got sort of probably 10 years now plus in software development, lifecycle, DevOps, and cloud. And I've always been fascinated by AI, right? The buzzword kind of captured me, and then I started looking into the actual maths underneath. And having done an engineering degree, I found, oh, hey, this is all just like, matrix multiplication. I can do this. Started, doing a bunch of online courses, building some AI models, etc. And then I moved to Seldon. Actually, well, I mean, within the year, but maybe more like 9 months ago now. I moved to Seldon, who are a production machine learning company. And it's been a real like baptism of fire, right? Suddenly going from being this guy who's like interested in ML and knows how to build stuff on my own machine to like, how on earth do we do this in production? So generally, a lot of the problems that you come across stem from this quote here, right? Which is that the way we do data science largely goes against agile principles. If you think about most software delivery, we're doing multiple commit, well, we're even using version control, right? That's a start. But then we do regular commits, we do test-driven development, we have CI/CD pipelines. We can automate pretty much everything. That's definitely not the case for the vast majority of data scientists. There are a number of issues, right? So the first thing is that a lot of the work is done in isolation. Companies tend to hire a data scientist or a bunch of them and say, oh, go and do AI because that's the next big thing, right? And so they sit in their little team and they grab some data. They normally extract it, like they don't work with live production systems for the data. They just request it and they get given it by another team, and then they do some modeling and they build a model and they say, hey, we can predict all this stuff. Great. But they're working totally in isolation. Most of the work they do is pretty much experimentation. They're building prototypes, testing out different models, different architectures, seeing what works. Very rarely do they reach a point where they go, this is the stuff I want to put in production. They spend like weeks, maybe months, just like optimizing tiny aspects of the model, which again, if you think about software delivery, right, we're taught with agile principles that we should just get a minimal viable product out and then start iterating on there when we get feedback from users. In machine learning, people are almost doing the exact opposite. They're trying to build like the most perfect model, and then they deploy it, and then only then, maybe like 6 months, a year later, do they start to get any feedback on whether that's actually going to work in a real world setting. And then there's pretty much a total lack of testing, right? There's no integration testing, unit tests don't get done. The only types of testing that data scientists are very good at doing is model validation for things like accuracy or precision and recall and so on. Okay, so that was kind of like the experiences I had. It's experience I've seen in lots of other data scientists. But actually now most companies are at the point where those siloed data science teams and who've built models, they're demanding value from them now. It's no good paying a bunch of clever people to build models that don't actually then get used in production. Typically what happens, right? So I don't know if people are familiar with Jupyter notebooks or not. Jupyter notebooks are essentially a Python experimentation tool. I don't know, maybe experimentation is unfair, but they're a really nice way to write Python code that also has comments and outputs captured alongside it. And in theory, right, they're good because you can kind of step through all your workings, display all the outputs and the code, and you can write Markdown alongside it, and then you can share it with other people, and then they can execute the same thing. So the theory behind them is great, and they're actually a really good IDE to work in for data science and machine learning, because as I said, a lot of the work is experimental. You don't write a line of code and then that's done, right? You often write a bit of code, try something, go back, edit the first bit of code, rerun that bit of code. So I've actually spoken about most of these comments I'm now bringing up. But the frustrating thing is that they're in theory reproducible, but they're actually not, because they don't capture anything about the environment that they run in. So if I take your Jupyter notebook and then just run it, maybe I'm running a different version of Python. Maybe I haven't installed all the right dependencies. None of those are captured alongside it. So it's definitely not the same as like a Docker container, which you can take and run and execute anywhere. So they're not hugely reproducible, and that makes them really difficult when you want to try and take them and put them into production. There's actually, so Google wrote an article on notebook best practices, which goes I don't want to say a long way, but maybe like a decent way along the lines of if you're working in Jupyter notebooks, to trying to do things that can make your code more production ready. So go and check that out. That's a link, and I'll share these slides with you afterwards if you're interested in finding out more. Okay, so you write some stuff in a Jupyter notebook, great, right? Got results, nice visualizations. My accuracy of my classifier is now 90%, whatever. It's time to deploy it. Okay, so the obvious solution is, I'm writing code in Python. I've got my ML libraries in Python. Let's use something like Flask, right? So, I split my code that I'd written in this Jupyter notebook, which is all in little chunks, and maybe I put them into Python files, and then I create a REST API with Flask, and all good, right? If you look at that code on the right-hand side, what's that, 20 lines of code? And I've got a route there on my /predict where if I send requests into that, it gets fed into my model, a prediction is run, and I get my prediction back as the output. So, and there's actually nothing wrong with this approach. It's generally can be used, and particularly as a first pass is a good way to get something out there. But as we start to scale, we're going to see so many issues with just building our own API and running our own prediction within it. So as I said, right, success. I've written a Flask API, I've written a model, deployed it, it's all good. And this is where things start to become really, really hard. I start looking at real data, and suddenly actually I don't just get handed a nice CSV with all the nicest clean data in the world. I have to make build integrations to database systems and things like Kafka, where I'm getting streaming data. There are also like missing values. I have null fields, empty values, inconsistent values, things where the types are different. I have inconsistent schemas. I might be retrieving user details from one system and they look totally different from how they do from a different system, even though they're supposed to be the same. Inconsistencies all over the place. And then you also have this challenge of feature engineering, which for those of you who are kind of DevOpsy but not familiar with machine learning, basically to train a model, everything has to be turned into a number, right? You can't give give an algorithm some text, right? All of those, the algorithms that work with text, convert those into numbers first so that the machine can do mathematical computation on it. So this is called feature engineering. It's where we take a piece of information and we convert it into numbers that are represented in some way that the machine learning algorithm can work with them. And so that might be as simple as if I have some tabular data, right, that I've retrieved from a database, and it's got a category in there. So I don't know if let's say I'm a retailer, and the category is like product category, and there might be shoes, tops, jackets, etc. I can't feed that text in, but what I'll do instead is I'll build a dictionary that says, well, if it's jackets, I'm going to assign it the value 1, and if it's a shoe, then I'll assign it the value 2, etc. And then I can give that as an input, and then my machine learning model can then run and train and infer on top of that. So you have this kind of feature engineering problem, but more importantly, like those features need to be reusable. I also have the issue of different deployment modes. So great, a lot of requests are just online. I send a request, get a response back, brilliant. That my Flask API can handle that. But actually, think again, let's use my retail example. You're working in e-commerce. Actually, a lot of the machine learning that gets done there is recommender systems. And these might run every day, every week to generate, products that we think you might be interested in. But it's run across a data set of like millions of users, and we need individual predictions for each of those. We can't just do them every time they log in, because that might be really compute intensive, and it also might take a long time to run that prediction. So instead, they'll run a batch of maybe like 1 million users every night. But now we need to be able to handle that. So we need to be able to scale that, deliver it in time, so that when everyone gets up in the morning and they check their email or log into the website, they can see the tailored products to them. We also have to deal with things like streaming data. So a lot of the machine learning use cases you see in audio and video are real time. If you have to break down potentially hundreds of frames per second, run inference on them, looking for objects in those frames, as you were doing, if you're building, for example, an autonomous vehicle, right? You have multiple camera sources. You need to be detecting objects, confirming it from different views on other cameras. There's a lot of stuff that has to happen in there, and it all has to happen real time. Okay, so on top of this, machine learning models can actually be really huge. If you look at some of the kind of state-of-the-art models, like the GPT ones and transformers from the Hugging Face library and stuff like that, the model itself is often tens or hundreds of gigabytes big. So it's not as easy as just saying, well, let's take the code and throw it into a container and deploy it, right? We have to think about, where do we store these models? How do we pull those down and run them in real time, or for inference on the cloud? How do we package and version them alongside the actual code that runs and deploys them? So, and then some of them, particularly if you're working with image data, for example, actually you might have requirements to use GPUs, so that for self-driving car example I had earlier, right, you need to analyze hundreds of frames in a very short space of time. if you're running inference on a GPU, you can achieve that, but on a CPU, you may not. So there are all of these kind of considerations you have to think about. And additionally, right, not necessarily every model is deployed as a single model, right? I might have an ensemble of models. So let me give you an example of that, right? If I have, let's say I'm building a machine learning system and I want to receive an image and tell you exactly what make and model of vehicle it is. Right, well, I could try and train a model on every single possible make and model of every vehicle type, but actually what's often more efficient is to train a high-level model that immediately classifies it as, okay, is this a bike or a car or a van or a lorry or a digger or whatever? And then depending on the result of that, sends it to the relevant make and model classifier for that type. So maybe it classifies it as a bicycle, and then it feeds it to a separate machine learning model that then takes the bike and analyzes it and says, okay, yeah, this is a Saracen bike of this make and model, etc. You have these kind of complex inference graphs, this requirement, and this can be done in all sorts of different ways, right? And I'll show a little bit more of that in a minute. Again, I mentioned the aspect feature engineering. So I gave that example of receiving categories and needing to convert that into numbers. Typically, that's done through a process called a transformer. So we take the input, we transform it into something that's usable by the model, and then the model gives us some output that we then transform back into something useful for a human. So if I have a text, I don't know, summarization API, right? People give you a paragraph of text and you want to be able to return to them a sentence that just summarizes what that paragraph is about. So the input transformer is going to take all the initial text from your paragraph, convert it into word embeddings, and don't worry too much if you don't know what those are. They're just numerical representations of the words. And then it's going to pass that to the model, run a prediction to predict what the next word is or what the sentence should be. But that sentence is going to come out in a bunch of numbers as well. So my output transformer then takes those numbers, converts them back into words, and then feeds that back on the API so that as a developer or user using that API, all I have to do is provide text and I get text back. But under the covers, right, the machine learning infrastructure is dealing with all of that. Okay, so there's a lot of problems, but thankfully, a lot of these aren't necessarily new. And that's where we think Kubernetes comes to the rescue. It's pretty much the de facto standard now across the DevOps world for containerization orchestration, which is I always think is a real mouthful when I say that, but yeah, basically anyone who's doing any containerized workloads at scale has pretty much settled on Kubernetes, which is great because it means the tool keeps getting better and better and people add more and more to the ecosystem. But we can take this and use it for machine learning, and it already solves a lot of those issues we have. So what we did at Seldon was we built a fully open source library called Seldon Core. You can check it out on GitHub, etc. I'll send a link out afterwards. But what it does at this kind of simplest level is it deploys and monitors machine learning models on top of Kubernetes. And in a little bit more detail, right, it containerizes a model and provides it as a REST and gRPC microservice. And then I guess a little bit more information again is that we also provide these highly optimized inference servers that run all the different types of machine learning model that you would want to run. So if I've trained a TensorFlow model, for example, I don't have to worry about what's the most efficient way to run that at scale. We've built the optimized inference server. We're using that under the cover, and you just provide the model, and Seldon Core will containerize it with the inference server, wrap it, and deploy it on Kubernetes as you would with any other deployment. So what does that look like? There are kind of two really important things you need to be aware of. So there's a Seldon controller, which creates these Kubernetes objects for the custom resource definition, which I'll comment onto. And then it creates the appropriate ingress rules to route to the deployments. And then we have this custom resource definition, which is the bit that you define as a user. You write this YAML file, and there's a really simple example of a deployment there, where I'm giving. If you look at down into towards the bottom where it says like implementation sklearn server, that's where I'm saying use the scikit-learn server that's already been built and optimized for running workloads on Kubernetes. And then just below that, there's a model URI just saying, okay, here's where my model is, go and grab it and deploy it, please. So if you're familiar with Kubernetes, this will seem really comfortable. Essentially, it takes it, deploys it, does the routing over the top so that you have a service and a deployment and the pods all running within Kube for you. Okay, we also, on top of that, can leverage all the great stuff that comes with Kubernetes, right? There are tons of CNCF tools. Why would we rebuild them when we can use them and integrate Seldon core into them for added value? So the first one is you can do request and response logging to Elasticsearch. This is actually really important because in the machine learning world particularly, people want to know what a prediction result was, right? And so we need some sort of auditability there to say, oh yeah, your prediction was this, and here was the input data, so that if we need to feed it through a different model or evaluate our models in the future, we've got that data. So yeah, we use Elasticsearch for that. You can stick it all into an ELK stack and have nice visualizations on it. We use Jaeger for distributed tracing. So again, integration in there so that you can view the microservice hops and the latency across all of your requests in there, which is again really useful for debugging, because once you get to the point where you're running hundreds of microservices on Kubernetes, it's really difficult when you just send an API request and your response takes 10 seconds to come back to know what's actually causing that. Is it the ingress controller? Is it the service? Is it the something in the pod? Is it the actual engine that's running the machine learning model? Is it just the model itself? Is there some slow code in there? It's really hard to know. So Jaeger and the Open Tracing Initiative are really good for that kind of thing. There's a built-in metrics collection and aggregation into Prometheus. So if you have a Prometheus server running on your Kube cluster, Seldon core will automatically pipe metrics to it. And we have a Grafana dashboard you can install that you can visualize all of that through. And then we integrate with Knative and Kafka to do stream processing stuff. And then the final thing is that batch processing workflow managers like Argo or Apache Airflow or whatever else, right? We have integrations to a lot of those to be able to do batch requests. Okay, so that's a lot of the DevOpsy side, but there are still a lot of other considerations we have. I'm just going to take a sip of water, one sec. So as I mentioned, these model files are one of the things. They can be huge. We have to version them, but ML deployments are not just code, right? So those models themselves, typically, we probably need a model registry around this. The generally accepted practice is that you store these in an object storage bucket, so like S3 or Google Storage or whatever, or Minio if you're running it on a local cluster. But you don't just manually stick them in there. You ideally should be using some sort of model registry. So one we see that gets used a lot is MLflow. It's another open source tool built by Databricks that versions and tracks all of your model training and then the actual model artifacts afterwards. And that's really useful because then you've got all of your models nicely versioned. When you come to deployment, you can pick up all the metadata and deploy it alongside the model. That brings me to my next point, right? Metadata. So there are a bunch of things you need to capture. The actual input and output schemas for the model itself. they vary massively by model, and you can think of them very much like you would treat an API definition. Every app you deploy has slightly different API endpoints, and those need documenting somewhere. It's very much the same for a model. We need to know, what data do we pass in, what format should it be in, etc. I talked about this feature engineering thing, right, which is the converting of data into a format that is more usable for a machine learning model. Increasingly, we're seeing a rise in people using a tool called a feature store, and there are a bunch of open source ones out there. The most popular is probably Feast, that gets used on Kubernetes quite a bit. The idea of a feature store is to allow you to reuse those pre-processed data for model training and inference as well. So sometimes it might be real time as well, like a request comes in and you then go and query the feature store and retrieve the relevant value for that. And then ideally we should be doing some sort of data provenance, right? The end goal for every production machine learning system should be to be able to say, this prediction that we provided to this user was run on this server or this pod or whatever container and whatever infrastructure you're using, which was serving this model at this version, which was trained using this code and this data, so that you have that lineage all the way back from the actual thing that impacts a user or your business to the original data that was used to build the machine learning model. And increasingly, that's becoming more of a mandated thing across highly regulated industries, but it's definitely a good best practice that people should be doing anyway. Okay, so all of these things need to be automated, be tracked and versioned, all the stuff that as a DevOps professional you'll be familiar with. Data science definitely aren't. A couple of things we like to do at Seldon. So we have adopted a GitOps methodology, I guess. We store all the manifests in Git, and then it allows us full recoverability and an audit trail as well for every single deployment that happens. We know how and when, and we can recreate it. Another cool thing we use is we have integrated with Iterate, which is an open source project that I think came out of IBM. And what Iterate allows you to do is to define well, they call it progressive rollouts, but it's a way to roll out new versions of an app, or in our case, a machine learning model, with some sort of feedback metrics on it that allows automatic promotion of that candidate. So in our case, it might be, I have a machine learning model that's running in production. I've trained a new version of the model. It looks good in all of our theoretical tests in the lab, but actually now we want to try and roll that out to production. How do we agree on what is a good point to promote it over the previous model? Well, one of the ways we could do that is if we used a progressive rollout to start splitting traffic or shadowing traffic to the candidate model, and then capturing responses on that. So your reward feedback might be infrastructure things like what's the latency and so on, but it might be more machine learning specific. So actually, if you're getting users to interact with your system, they might be able to tell you whether predictions are correct or not. And if you're getting that feedback and you kind of complete the loop on that, what Iterate will do is you can set a metric, let's say the accuracy for one model needs to be above 90% in order to replace the previous model. And so we can get that live feedback from the actual users using the system, telling us, yes, the predictions are correct. And then Iterate will automatically promote that model once it's achieved that level of accuracy for a certain amount of time that we've defined. So that's something we find really cool, because it kind of deals with the challenge of automating these rollouts, which typically most people do very, very manually. We also have to monitor models for some data science type concepts. So yes, you have all the infrastructure level monitoring, latency, CPU, memory usage, etc. But the machine learning models are different from applications in that they, like, what they're set up to do is to infer some sort of correlation between inputs and outputs, right? And almost in almost all cases, what they're trying to predict is some sort of real world phenomenon. So, whether it's like somebody's risk when applying for a loan, or whether it's, as we said in the driving car example, self-driving car example, is that person about to cross the road, etc. The problem with that is that everything in the real world changes. So inevitably, your machine learning models drift over time. And so a good example of this might be in the pandemic, you have trained a house price model predictor, and it very accurately tells you, if you put in the number of rooms, where it is, how big the garden is, etc. It'll tell you how much the house is worth. But we then have a global pandemic, and people don't want to live in pokey one-bedroom flats in central London anymore. They all want to move out to the countryside, and they want to have lots more space, and they definitely need a second bedroom because everyone's working from home. So suddenly your model is now out of date, but you have no way of knowing that from an IT standpoint. But you can monitor for things like drift, and other things might be outliers in there as well. So actually, maybe my model is very accurate, but we don't know every possible use case that might get fed into it. Someone might say, actually, I've got a house here with 19 bedrooms and 40,000 acres of land, and at that kind of outlier level, we're not sure whether our model is accurate or not. So we might want to flag for those for manual investigation, etc. And the other thing is we might want to monitor for adversarial attacks. There's been quite a lot of research and interesting articles that have come out showing that, for example, if you change a few pixels on an image, you can trick a machine learning classifier into thinking it's something totally different. So ideally in production, we need to be monitoring for those kind of attacks to try and spot them and then take remedial action. So the good news there is that, again, you don't have to worry too much about it. We have dealt with this problem already as a company with all of our customers, and we built an open source library to do that. So Alibi Detect does machine learning monitoring for drift detection, outlier detection, and adversarial detection. So the 3 use cases I just went through. Again, check that out on GitHub. It comes as a standalone Python library, but it's also integrated into Seldon core. So if you're deploying models on Kubernetes, you can deploy the monitoring algorithms on top of it as well to spot things like drift. And then there are yet more headaches. So I'll go over these fairly quickly because there are lots more things. But what I have glossed over so much so far is actually the training of the machine learning model. That is resource intensive. It often requires different hardware and needs to be distributed as you have vast training data sets, and they might have to run across multiple GPUs, and it might take a long time. I talked about how testing is pretty much non-existent for data scientists, but it's still a headache we have to achieve, right? So how do we educate people to do to write unit tests for their code, to do regression tests and integration tests as we roll into production? I mentioned that data science is probably better at this, but we still have to do it, and we should be automating this as much as possible. And model evaluation for what's the actual accuracy of that model, depending on the type of model. So for things like let's say a language translation model, something that takes French text and converts it into English, accuracy, it's very hard. What even is accuracy, right? So there are different metrics depending on the type of model. For that one, we use something called word error rate, which is basically, what the percentage of the words that it got wrong from the source language into the destination language. And then we also have to optimize these models for the destination hardware, which can be totally different, depending on where you deploy it. So what a data scientist runs on their laptop might be totally different from the production environment within your Kube cluster. So being able to optimize it for the infrastructure underneath is really important, and there are lots of cool open source libraries from NVIDIA and OctoML and people like that who are doing a lot of good work in that space. And the final thing I just want to touch on that you should be aware of and should definitely think about when you're deploying models in production is that increasingly people are demanding explanations for models, and it's a tricky field, right? Because we're never going to be able to exactly say why a deep neural network made that exact prediction, but we can do some pretty good approximations, and there are some very good algorithms out there that will do that for you. So there are two different ways you might do this, right? One is the model view, which is let's try and explain at a high level, how does this model make predictions? And then there's also the instant view, which is sort of coming at it from a different approach, which is what you're saying in the instance view is, I have a particular prediction that I have received from this model. How did it come to that conclusion? And so we're trying to understand, what were the most important features in making up that prediction. There are lots of different algorithms for different types and modalities of data, because some cover text, some cover image data, others cover tabular and numerical data. The good thing is, again, like we did for monitoring, we built an Alibi explain library, which encompasses all of these explainability algorithms into one nice Python library, which again, you can deploy alongside your models on Seldon core. So do check out that. As I mentioned, fully open source. It has explainability algorithms for both white box and black box models. So white box models being ones where you have access to the actual model weights and understand how it was trained, and black box models being, I have no idea at all. I basically only have an endpoint, but I still want to make some sort of explanations. I mentioned the different global and local views, and then it handles classification and regression models. Just a note on the explainability, like I would love to see it being used more in production for particularly for end user type situations where predictions are being made. So if I could renew my car insurance every year and it could tell me, because they're all using machine learning models underneath to to come up with the quotes and the valuations and assess the risk that I'm going to be to the company and so on. But if they could tell me, here were the three strongest factors that contributed to why your insurance is more expensive this year, I would probably find that a lot more comforting than just, hey, your premium's going up by 100 quid. And then I just think, oh, you guys are just screwing me, so I have to go and look elsewhere. And those are the kind of use cases that it would be nice to see more of. There are also more like regulated ones, like in banking now. They're looking at whether explainability should be used or mandated for life-changing decisions like mortgage approvals and loan approvals and things like that. Okay, so that's a lot of information to take in. As I've kind of alluded to, right, this is a pretty confusing space. There's lots of stuff going on, but you don't need to take just my word for it, right? Matt Turk did the hard work to put together this MLOps landscape, right, which shows all the different aspects of machine learning in production and the things you have to worry about, and then all the tools and vendors and so on that tackle all the different spaces. So as you can see from here, right, it's an incredibly confusing space, but that doesn't mean we can't simplify it. So my golden rules are very much like follow DevOps best practices wherever possible. I like to use open source because it means we can contribute to it and make it better. And I guess the second or third one, I've said two already, is that follow agile principles as well, right? Instead of spending months building a model and iterating over and over to try and get the best accuracy on your test set, which isn't real data or might have gone out of date by then, build something simple, get it out there, and then see how users interact with it, because that's when you'll start to get the really valuable data from the system. So with that, I will just say thank you very much for listening. That's a lot of talking and a lot of stuff to take in. If you have questions, please ask them now, or you can email me or ping me on Twitter or LinkedIn. So yeah, thank you.
Okay. Thanks, Ed. So we do have a couple of questions that have come in just now. We'll just go through them at the moment. So one of the first ones I've got here is just with the bulk of ML computation being asynchronous, is there anything you can point towards in terms of like unit testing, integration, and end-to-end testing, which tends to be synchronous rather than asynchronous? Is there any tools that could help with that side of things?
Not particularly is the answer, right? And it's still, yeah, the testing is by far the weakest space for production machine learning, and by a long way, right? And there are lots of vendors now building tools for, with Seldon, we built these open source libraries and open source them, but we actually, we also have an enterprise product. So we wrap all of those together, we build a UI and loads of integrations into it and so on. So our mission as an MLOps company is very much to solve the model deployment challenge for people. And there are other ones tackling, the feature stores or, data provenance and versioning of models. And there are none that I'm aware of who are really tackling the testing space. And so, yeah, I would love to know if you find things, let me know, because it's a big gap in the market right now.
Yeah, I think in terms of the only sort of testing stuff I'm really aware of is just when you're actually doing the model training, where you've got that known set of data and known outputs, and setting aside parts of it, whether that's just a straight split of like an 80-20 split of your data, or randomizing it, to actually have the data that you know there used to test the accuracy of the model, but not in terms of the actual deployment side of things.
Yeah, and so that, like, by nature of it, is it's pretty much synchronous, right? And it's, as I said, you can often end up spending months building the model, and your test set is out of date, and it may not have been a real world example in the first place. I think that's partly why we do that work with Iterate, to that integration there, to be able to do progressive rollouts, is that you've just got to be really careful rolling out new models into production, because you don't exactly know what happens underneath. It's not like an app where you know every line of code and you can account for what it's going to do, and it's going to behave the exact same every time. So the more you can do A/B tests, canary, shadows, etc., and get them into a like semi-production environment first, where you can start evaluating them, the better. But there's very little, for automating that at the moment. I think most teams do it manually, with data scientists watching very carefully every time they do.
Yeah, I'm sure that there are some solutions in there around just like traditional testing of actual like known data going through the endpoint. But as you say, it's a complex topic.
Yeah, you can use traditional testing tools, and you can say like, you can assert things like, if I give it, I don't know, pick another example, like, I talked a lot about like loan approvals, right? If I give it all this data, it should approve my loan, right? And you can have a bunch of, preset personas, if you like, that you fire through the system and check, and because that way okay, all of these users were approved loans, they should be approved loans. If they don't get approved, then we know we might have an issue with the model and we need to look at it. So you can do sanity checks like that, but it's hard until you really get it into real world and start getting like thousands of new requests to know exactly how it's going to perform.
Yeah. Okay, so I've got another question here. So what would you say is the benefit of using open source components rather than some of the sort of big cloud providers, like even with Databricks or with SageMaker from AWS?
Yeah, so yeah, that's a good question. Comes up a lot. I'd say I wouldn't. So I actually don't think you should just use open source. I think it depends on the scale that you're working at. I think if you're a small team, maybe working for a startup or a small company, or you're just doing a few things that don't need to scale very much, you're probably better off using, as a AWS, Vertex on Google Cloud or something like that, the SageMaker tools, but you've got everything in one place, right? The problem comes when you start to scale and you've now got multiple machine learning teams around your business. So actually, because of the work we do at Seldon, right, with the open source stuff and now an enterprise product, the vast majority of our customers are really big enterprises. They're people like drugs manufacturers who have thousands of different models they deploy all the time to try and identify, what could be the appropriate molecule to start a new drug discovery trial on. Now, when you're that kind of scale, that you'll find that things like SageMaker and Vertex are really limited in what you can do. You can't build these really, really complex inference graphs where you've got, hundreds of models and you automatically select the most appropriate one for things. And that's where, you could use, for example, Seldon for the model deployment, because that's pretty much all we do as a company and we do it really well. But then you might go use, I don't know, a totally different vendor or a different open source tool for something else, like, model versioning. Maybe MLflow is like the gold standard that you want to use. And then for a feature store, you'd use something like Feast. So once you reach a certain size, I think you'll have bespoke requirements and you need to go after the best of breed in the space and build your own platform. But until you're at that size where you need to build a platform, then, by all means, the cloud providers make it pretty easy and you can get stuff done pretty fast on that.
Yeah. So, and just in terms of what you mentioned there about the enterprise tool, so I think obviously that's a revenue stream for Seldon, but what's your motivation behind using open source or providing open source?
I think it's I guess in the first place, it's an engineering one. So actually, as a company, Seldon did not set out to provide tooling. They were started as a natural language processing ML company. And then what actually happened was they realized they had to build all this tooling to be able to roll things out properly. And so they started building, they wanted to deploy stuff to Kube, but there was nothing there and it was hard. So they started writing a CRD and then they wrote an operator and stuff like that. And they were like, actually, we feel like that was a bigger problem to solve than the initial, doing some natural language processing on legal documents. Because of that, right, the engineering team were keen on open source. We're using Kubernetes anyway, now built their own thing and open sourced it and other people were contributing to it. It was the obvious thing for us. We strongly feel that it drives adoption and it helps us build the best tools because other people help contribute. People are much more welcoming and open about providing feedback and we can just iterate and make it better and better. So yeah, that's generally our approach to it. And that's why we're an open source first company, I guess.
Excellent. And just in general, in terms of MLOps, what do you see as the future of MLOps? What sort of things do you see coming down the line?
Yeah, I think we'll see, so hopefully more stuff around testing, right? We've talked about that already. But I think we'll start to see stacks emerge, a bit like you have, your mean stack or your MERN stack or a LAMP stack and things like that, right? For software development, and you have your ELK stack and your Cube and Prometheus and Grafana type things in the DevOps world. You'll start to see a predefined set of open source components that work well to provide that end-to-end thing. And there's a project called Kubeflow that have kind of tried to approach that, and it's been a bit neglected because Google created it and then they sort of abandoned it, and people in the community have tried to pick it up and run with it. But that aims to do it, right? It aims to pull in different open source things, combine them into one platform that runs on top of Kubernetes that allows you to spin up Jupyter Notebook environments, to version your models, to deploy them, and they use Seldon under the covers to do deployments on that. So yeah, I think we'll see that. It might be whatever it is, MLflow plus Pachyderm plus Tecton plus Seldon is like becomes a stack, and then there might be another competing stack that people use for slightly different use cases, like I don't know, streaming data or whatever. So yeah, I think that's probably where it'll go in the next year or two. And there'll also be, I imagine, probably quite a lot of acquisitions. So you might see the likes of you know, Databricks or Algorithmia like acquiring a combination of those vendors who maybe build up a stack, and then you know, pushing that as more of an end-to-end solution as well.
Cool. Yeah, no, I think that's maybe you can get some acqui-hires as well, which like they're buying them for the individual people there rather than the technology, which it is an open source thing, might not be great.
Yeah, for sure. That's, I mean, if you think like, you know, DevOps is a high and in-demand skill, MLOps is like, you've got to have the DevOps skill and you've got to have an understanding of machine learning stuff as well, both of which are a hugely in-demand thing. So you can imagine how hard it is to hire in this space, which, by the way, we are hiring if you're interested. Come work at Seldon. But who isn't at the moment?
Yeah, exactly. Yeah, the IT market in general just is crazy just now. But no, I think that's all the questions we've got just now. I think we're just going up on time. So, yeah, thanks very much, Ed, for the talk today. It was really interesting, and I hope everyone that joined enjoyed the talk from Ed today. And what we'll do is we'll send. Sorry, yeah, when you go ahead.
No, I was just going to say thank you so much for having me. It's been a pleasure. I'm sorry I couldn't get my webcam working with this, but yeah, I don't know. You can Google me. You'll see my face somewhere.
Yeah. So what we'll do is after this call, we'll send out the recording and the slides to the meetup group so that they're available for everyone.
Cool. Sounds good.
Yep. Right. Thanks everyone, and hope you enjoyed it. Thanks all.